So back in 2017, a group of 8 researchers at Google dropped a paper with this, deceptively simple title. Little did they know, they were basically publishing the blueprint for what would become a multi-trillion-dollar AI revolution. This is the story of that paper. Attention is all you need.
Okay, so to get why this paper was such a big deal, we have to start with a really basic question. How does a machine actually read? I don't just mean recognizing letters, but how does it understand context and meaning and the relationships between words?
For the longest time, the best AI models, these things called recurrent neural networks, or RNNs, they read kind of like you'd read an old stock ticker. It was just one single word at a time, in order. The model would see the word the, and it'd think about it. Then it'd see quick and update its understanding, then brown, and so on and so on.
And right away, you can probably see the huge problem this creates. If you have a really long sentence, the model might literally forget what the sentence started with by the time it gets to the end. It's like having a really bad short-term memory. Trying to connect the first word to the last word was this massive challenge, and it had a name, the sequential bottleneck.
And you don't have to take my word for it, the paper itself lays this out perfectly. In this table, n is just the length of the sentence. For those old recurrent models, the work it takes to connect 2 words goes up the farther apart they are. That's what O of n means. But just look at self-attention. O of 1. Constant time. It takes the exact same effort to connect the first word to the second as it does to connect the first word to the 500th. That's not an improvement, that's a whole new ballgame.
Now, to try and fix this memory problem, researchers had already invented a pretty clever patch. It was called an attention mechanism, and it was the special little add-on that let the model kind of peek back at important words it had already processed, even if they were way back at the beginning of the sentence.
But here was the problem. This attention thing was just bolted on to the side of the old, slow, one-word-at-a-time model. It was like putting a turbocharger on a lawnmower engine. Yeah, it helped, but the fundamental bottleneck, the slow part, was still right there at the core.
And then this paper came along. And that title, it wasn't just a title. It was a thesis. It was a bold, radical statement.
The authors asked this absolutely brilliant question. What if that clever patch, that attention mechanism, what if it wasn't just a patch? What if it could be the entire engine? What if you could just get rid of the slow, sequential part completely and build a model using nothing but attention?
And that radical idea is exactly what they built. They called it the transformer. As they say right in the paper's abstract, it's a brand new design that completely gets rid of recurrence. This is a model that can look at every single word in a sentence at the exact same moment. Everything, all at once.
And here it is, the diagram straight from the paper. Now, I know it looks a little intimidating, but the idea behind it is actually pretty simple. On the left, you've got the encoder. Its job is to read and really understand the sentence you give it. On the right, you've got the decoder. Its job is to take that understanding and generate the output, maybe a translation into another language. And the engine driving both of these halves? You guessed it, attention.
All right, let's zoom in on the heart of this thing. On the left, that's the basic building block. The paper calls it scaled dot product attention. That's the part that lets one word pay attention to another. But the real stroke of genius is what's on the right. The authors figured, why use just one attention mechanism? Why not run a bunch of them at the same time, in parallel? And they called that multi-head attention.
The best way to picture multi-head attention is to imagine a panel of experts all reading the same sentence at once. In the original paper, they used 8 of them. So one expert might be a grammar specialist, just looking at verbs and nouns. Another expert is only focused on tracking who did what to whom in the sentence. Maybe a third is looking for word associations. By having these 8 heads all working in parallel, each with its own focus, the model gets this incredibly rich, layered understanding of the text in a single pass.
So how does this attention actually work under the hood? Well, it's kind of like a 3-step dance. For any word, it sends out a query. Think of it like that word shouting to the rest of the sentence, hey, who here is relevant to me? Then every other word holds up a key, which is like a little sign advertising what it's about. The query looks at all the keys, finds the best matches, and those matching words then offer up their value, which is their actual meaning and context. This little dance of queries, keys, and values happens for every single word, all at the same time. It's beautiful.
But wait a second, if you look at all the words at once, how in the world does the model know the difference between dog bites man and man bites dog? The word order is gone. This is where the authors came up with another brilliant, elegant solution: positional encodings.
They basically add a tiny, unique signal to each word. It's generated using sine and cosine waves that acts like a GPS coordinate, telling the model exactly where that word stands in the lineup, first, second, third, and so on. So, okay, this all sounds amazing in theory, right? A parallel design, these multi-headed experts, clever mathematical tricks for word order, but here's the billion-dollar question. Did it actually work any better than the old models?
It didn't just work. It absolutely shattered the records. On the standard English to German translation test, the transformer hit a blue score, which is just a way to measure the quality of a machine translation, of 28.4. Now that number might not mean much, but it blew the previous best models on the planet out of the water by more than 2 full points. And in this field, a 2-point jump is an earthquake.
And it wasn't a fluke. They tested it on English to French translation, and bam, another new record, a score of 41.8. The transformer wasn't just a little better, it was in a completely different league. But honestly, this might be the most mind-blowing part of the whole paper. The transformer wasn't just better, it was ridiculously faster and cheaper to train. While the other top models took massive amounts of time and money, the transformer, it hit its record-breaking performance after just 3.5 days on only 8 GPUs. That's, as they put it, a small fraction of the cost. Better, faster, and cheaper? I mean, that's the holy trinity.
The authors themselves really summed up their achievement perfectly. They created the very first model of its kind that relied entirely on self-attention. They prove you could just throw out that old sequential way of thinking and still get world-class results.
So why does a paper from 2017 matter so much to you today? Because this architecture, the transformer, well, it's the T in GPT. It's the engine humming away inside pretty much every single large language model and generative AI tool that we use every single day. This is where it all started.
Think about this. The authors of this paper trained a model with a few 100 million parameters on just 8 GPUs. That was 2017. Today's models have trillions of parameters. So it leaves you with this one kind of staggering question to think about. What happens when you take this revolutionary idea and you make it 1 million times bigger? Well, we're finding out the answer to that question right now.